All right. Well, now that we have the idea of protons and neutrons and electrons, um, that opened up a whole can of different ideas and and possibilities of how atoms could be. And it turns out that what we use to identify an atom as a specific atom, carbon, hydrogen, helium, whatever it is, has to do with the number of protons. If an atom has the same number of protons as any other atom, then that means that that atom is exactly the same thing. So it's the protons that identify an atom, sort of its student ID number or its social security number. It's the number within it that describes it and identifies it as a particular atom. However, an atom doesn't have to, for a particular type of atom, doesn't have to have the same number of neutrons or electrons, and we'll get to that later. But it doesn't have to have the same number of neutrons. It has to have the same number of protons, but the neutrons could be whatever. Now, when you have two atoms of a particular element, and they happen to have different number of neutrons in the nucleus, excuse me, that's called an isotope. And again, the protons have to be the same, but the neutrons could be whatever. So when you have isotopes, what it does is that it causes for a variety of elements to have a variety of different possibilities. So for example, here's a little list of some. Iron has three kinds of isotopes that exist in nature. Manganese doesn't have any choices, it just has one kind. Hydrogen, 3, antimony, 2, chromium, 4. So why an atom has 1, 2, 3, 4, or whatever number has all to do with how that nucleus is and if it's stable or not. But these nuclei, the plural of nucleus, can have different number of neutrons. So how do we deal with that? How do we figure that out? What does an atom have? So in nature, we don't have to do anything necessarily. All these options are out there. Nature likes to have variety. And so for any given element, there's different amounts of each of isotopes that it has. And every atom is different. For example, I give you silver. Silver has two isotopes, 107 and 109. And one of them exists 51.839% of the time, and the other one exists 48.161. Together that adds up to 100%. So out of 100%, it's almost a 50-50 of these two different kinds. Now, every single element has its own unique balance of the percentage of the isotopes, and there's nothing fixed, and there's nothing that it has to be. It just sort of is what it is. And so when we think about isotopes and how we show what the different kinds there are, how do we show that? And that's what's called a notation. So again, the number of protons in the nucleus is called is what we use to identify an atom. And that is a fixed amount, and we call that the atomic number. And then the symbol that we give for that atomic number is a Z, and you'll see where that Z comes in. The number of protons plus the neutrons, which is the bulk of the mass of an atom, is what's called its mass number. So if you add up the protons and the neutrons, you get the mass number, and we give that a symbol of A. Now, there's a couple of ways that we can show that. One way is in this method, which you'll see a lot, shows the element's symbol, whatever it happens to be, and then the mass number up on top as a superscript, and then the atomic number Z as the subscript. Okay, and remember, the atomic number is the number of protons, the mass number is the protons plus neutrons, and all the way here on the top right is if the atom has a charge, which we'll get to. That's where you show it. Okay, so mass number on top, atomic number on the bottom. Okay, and I'm going to come back and show you a couple of examples.